G'day. The Common Core state standards have a whole series of plus standards on vector and matrix algebra. Now, this is actually very tricky stuff to bring into the high school curriculum. I don't know a very natural way to motivate this material in a way that's, gets into the significant depth that the Common Core state standards seem to demand, but without the full tools of taking a linear algebra course or something like that. So it's very tricky to motivate this work, in my opinion, for high school students. But I have some ideas. So what I want to do here is just put together a quick suite of videos on a possible approach. Actually, we've got three possible approaches that actually have three storylines, so I think we should do all three that come together into one sort of beautiful whole that I think might have context and meaning for a high school student too. All right, so these are a bit rough. Just going to have to deal with me and my fast talking and my messy board work, but I just want to get these ideas out there so that you can consider, if you're writing a curriculum on these matters, here's a possible idea to consider. Right, here goes. All right, idea number one to get matrices on the scene for high school students. So, if you call it a permutations and combinations class, you often start off with something called the multiplication principle. We've got A ways to do one task, B ways to do a second task. Then if those choices don't interfere with each other, there are A times B ways to do both tasks. And often a standard example to get started on that is something like the following. Suppose there's a city 1 and a city 2 and a city 3, and they basically just say essentially three routes to get you from city 1 to city 2, maybe three major highways. Or to get from, city 2 to city 3, maybe there's essentially four different ways to get from 2 to 3. And to motivate the multiplication principle, you might ask then, how many ways can I get from city 1 to city 3? Well, there are three ways from 1 to 2. Each of those choices has four options from 2 to 3. Three groups of four options makes a total of 12 options. 3 times 4. All right, that's great. So that's a concept that appears in a permutations combinations class. A ways, B ways, A times B ways in total. But then you can actually take a diagram of this and have some fun with it. Well, there's a fourth city, say down here. And suppose there's, say, one way to get from city 1 to 4, and then two ways to get from city 4 to 3. Now, the total number of ways to get from 1 to 3 is now a little more complicated. I can't just do an ordinary multiplication principle. I have to divide it into parts and think my way through it. Or I can make the problem even worse. What if I made a really complicated network diagram, had like an extra route twixt 2 and 4? And maybe there's like a little joy route you might want to take out to the countryside that takes you out from city 1 and back again. All right. Or I can make matters even worse. What I've done all these is one-way highways going a certain direction. Suppose I actually some of these go backwards as well. I can actually go from 3 to 2 this way, or 4 to 1 this way, or something like that, or 3 to 4. So now I've got a very complicated network diagram of routes between cities. Maybe it's like a map of airline routes or something across the nation. That on any given day, there are two flights that go one way to 2 and 3, another way, and there's two flights going from 3 to 2. So I might start asking now complicated questions. How many direct routes are there from 1 to 4? In this picture, none. Okay, how many indirect routes are there from 1 to 4 if I'm allowing myself one stop along the way? Well, there's a couple. There's that and that and that and so forth. Well, how many ways do they get from 1 to 4 if I allow myself two stops? Maybe if I want to go for the really cheap airline fare, I'm willing to do up to 2 stops. So I actually start asking complicated questions about network diagrams like this. All right, if it's a really complicated network diagram, however, I'm probably going to want a computer to do it, and drawing these diagrams gets really messy, very complicated, and very hard. So the question is, how can I incorporate that information in a more sort of systematic way that's easier to enter in a computer or for me to sort of handle rather than having messy lines all over a page? Well, it seems natural then to just, draw a table of values. I mean, how many routes are there from 1 to 2, from 1 to 3, 1 to 4, blah, blah, blah. So let me do that. Let me draw a table of values. 1, 2, 3, 4, cities 1, 2, 3, and 4, cities 1, 2, 3, and 4. How many routes are there from 1 to 1? Well, I guess we've got that country go for scenery ride route. How many routes are there from 1 to 2? So I'm always doing from this city to that city. It's just a choice, I decided to go that way. How many routes from 1 to 2? Looks like I've got 3 routes. How many direct routes are there from 1 to 3? I've got no direct routes from 1 to 3. I've got some indirect ones, but no direct ones. From 1 to 4, none. For city 2, any ways to get back to 1? 0 ways to get back to 1. Any routes from 2 to itself? Nope, no joy rides from 2. 2 to 3, 2 routes, 2 to 4, 1, and so on. So I'm actually encapsulating all this information in a table. Finish it off, 3 to 1 is 0, 3 to 2 is 2, 3 to 3, there are no loops, 3 to 4, I've got 1, and 4 to 1, yep, there's 1, 4 to 2, none, 4 to 3, 1, and 4 to itself, none. All right, so here's a table, I'll call it P, the pathway table. This table encapsulates all the information on that graph. And just to be really clear, for example, if I wrote P2 2, 3. That's a standard thing, row, column. Row 2, column 3. This is the number of paths from city 2 to city 3, and according to my table, it's 2. And just to check, how many paths are there from 2 to 3? According to the picture, there's 2. All right, some language. That makes perfect sense. I've now encapsulated this in a lovely table. I actually don't need the sort of surrounding marks. It's really this table of information right here. Now, the science world uses the word matrix, especially geologists and archaeologists, for the sort of the background matter that holds, stuff in place. For example, if you're a geologist and you find some rock with crystals scattered through it, they call the background matter the matrix for that rock. All the crystals are held in place by this matrix of other conglomerate stuff. So the word matrix means something that holds stuff in place. So mathematicians actually use the word matrix for a table of values like this. It's sort of all the information is held in place in a beautiful table. So mathematicians call an array like this, and they might put curly brackets around it, just a style thing, it doesn't matter. And I might say the matrix P is given by this. In fact, this might be even called the root matrix or the path matrix for this particular network. Or actually the term they really use is the adjacency matrix, but language doesn't matter. All right, so that's it. And what I mean by here, when I write Pij, I mean the number of paths that go from city I to city J. So P3, 1, P was 3 and 1, 0. There are no paths from 3 to 1. Correct. All right, that's all a matrix is. That's idea number 1. But I'm not going to let this idea go because mathematicians actually do interesting mathematics on these things. So that's what I want to do next. Some interesting mathematics on my adjacency matrix for a network. So I have a little break here and we'll go to the next video.